IMAX-SFlow2D is a depth-average numerical flow model for pyroclastic avalanches created by Mattia de Micheli Vituri, Tommaso Esposito Ongaro, Giacomo Lari, and Alvaro Aravena, and here adapted into manageable cells for our use. IMAX has a few specialized parameters for pyroclastic flow. In this case, we'll quickly import the necessary Python packages, which we need, before we run the notebook. Once we get to this first cell, there are a couple of parameters which we can set to our liking. Obviously, we have a parameter for the name of this run. In this case, I'll use Mauna Loa since that's the example I'll be using. We also have the option to start from a previous run if we wish, but in this case, I'll start fresh, so I'll put F for false in this case. We also have a starting simulation time, an end simulation time, and a delta t, delta time, in between our output snapshots. It'll determine how frequently our snapshots are being output. We also have a handful of flags here. In this case, they determine whether we'll have conservation, whether we want the program to use an SRE, ASCII, DEM, a physical variable, and whether we want a max runout at each DT. Our last line here will allow us to select the verbose level. So we'll run it as that. I have a couple of defaults set in. We'll give it a second to run and make sure that that works before we continue moving forward. All right. Now that it's run, we can keep going further down. In this case, you as the user can also set parameters for our radial source. We have parameters here for location as well as the radius of the source that you wish to simulate. We also have a velocity for the source that you're simulating and the temperature of the source. And then we have a handful of parameters here which are all related to time. In this case, the first parameter will define the period between two cycles of pulsating flow. The second will define the duration of radial flow, and in this case, the difference will be the pause between the two pulses. We also have a third parameter, which defines the time required for the radial source to increase from no flow to maximum flow, and vice versa. And then the last parameter here will include the total duration, will determine the total duration of our radial source. I'll use these set defaults that I have here, and we'll keep going. Down here, you can also input some additional parameters, which will determine the granularity of each cell. You're all welcome to change them as you need. In this case, I have set them to we have them set to defaults, which will assure reasonable granularity, but you are welcome to make changes to this one as well. Once we get down here, we also have a DEM and vent check. In this case, we can pick our DEM and it'll check it for us. I'll use Mauna Loa again, but of course there are a handful of DEMs that you're welcome to select from and model yourselves. And you can do those by simply changing this DEM input. So I have a DEM for Mauna Loa, and it's loading up perfectly, which is great for us. Below here, we have the thermal parameters for the lava in our simulation. In this case, we have emissivity, the atmospheric heat coefficient, the expected fraction of area, the specific heat capacity, we have an N value that we can set, the temperature of the environment and of the ground. We have the thermal conductivity of the lava, thermal conductivity of the soil, an M value in this case, determining the viscosity. We have a density of soil, specific heat of soil, and the current temperature of the soil in our simulation. I'll use these values for the purposes of my run here, and we'll keep going down. We also have a handful of numerical parameters which can impact the stability of our solution, so handle these with caution. We have a handful of solver schemes you can choose from, and we list them out here. You can set the CFL, you can set the limiter, in this case for the slope of the linear reconstruction, and then you can set the slope coefficient, also for the linear reconstruction. More information on these specific methods can be found in the documentation. And then, of course, right underneath this, once we run that, we can also set the gravity of our simulation. If you wish to simulate for another planet or wish to simulate on the moon, you are welcome to do so by simply just make sure you change the gravity for your simulation. We'll keep the gravity of Earth for the purposes of this, and we'll keep moving forward with our example. We have a handful of rheological parameters down here, which you 100% should, they can be adjusted and probably should adjust as needed. We have a handful, we also have a few of the values here, including a viscosity parameter, a reference kinematic velocity, a reference temperature, and the yield strength for lava rheology. We also have a handful of models which we can use here and select from, which in this case I'll just be selecting the third model. Right underneath here there are a handful of parameters for gas, which you can change if you are trying to consider degassing. You can feel free to change these parameters and incorporate them into the model as well. Once we get past our gas parameters, we can run the next couple cells without changing anything. Once you set in your parameters, they will be input into these couple of cells, just using the variable names, and they should allow for the model to run by itself. Once we run these 4 cells, we will have a couple of outputs that we can utilize. This cell will explain what time steps we can pick from. It'll print it out at the bottom once it runs, so we'll give it a second. It might take a while, which is a good sign. If the model runs too quickly, it's likely spitting out an error message back at you, so you can comment out the last parameter down here and see what exactly is coming out as an error. We'll give it a second to run. So now that everything is run, it'll tell us how many time steps we're able to visualize below. So we can pick one of the time steps. In this case, given my dt and given this time of our simulation, we have 4 time steps. They start at 0, we can go all the way up to 3. We'll, in this case, for the example, we'll visualize time step 2. So once we pick a time step, we can run the rest of this all the way through. And once we get to the very end, it should plot this for us and spit it back out. Obviously, there are a couple things you can change about your plot at the very end here. You can change the different axis titles, as well as a couple of the labels and what it's deciding to save this figure as. I'll save it as maunaloa.svg, but you are all welcome to save all of your visualized plots as whatever you wish to for the purposes of your own research. Might take a second, which is to be expected, so we'll come back once it's done. So now that it's finished running, we'll have a wonderful visualization here, which we can see here. Of course, this notebook specifically will also spit out a handful of snapshot.asc files, which you're welcome to look through. And it'll save, as I mentioned, it'll save our plot over here as a handy SVG file, but again, you're welcome to save it as you need and in whatever shape you would like to use. For more information on the numerical methods which we used here, you can refer to Biagioli et al. 2023. That paper is very handy for getting to know more about the numerical methods at hand. And you can find that fully cited in the IMEX section of our documentation at victor.readthedocs.io. Yeah, thank you for listening to this tutorial.